we're this girl, she works at the Asian buffet. She has a random sample of receipts that has both the tip size and the amount of time that people stay. And she thinks that people that stay longer tip more. So we're going to figure out if that is indeed true based on the sample that she is given. But first we have to answer some questions. So first of all, I want to look at the regression line. It looks like it has a positive slope. Maybe it could be fairly strong. We're not sure yet until we look at our actual R value. So we're going to do that. So we'll look at the, first of all, let's answer A. That'll get us rolling really nicely. What is the equation of the least squares regression line? So y hat is going to be, remember, this guy is our slope. And that is our y-intercept. So 0.03013 x plus 4.535. That's our y-intercept. Define any variables that we use. So this tells us that, so our slope tells us that we expect the tip to increase by 3 cents per minute. And this, our y-intercept, right, essentially tells us that if a person stays for 0 minutes, we would expect the tip to be $4.50, which is weird. That's a strange. Sometimes the y-intercept doesn't really stop. Okay. We interpreted the slope already. Done. Explain what the value of r squared means in this setting. So r squared is here, right? And we're going to call that 0.132. And that, remember, that is our r squared value tells us the percentage of variation in y. That is caused by x, pretty much. There's a better way to say it. That's why I paused. I guess it's fine. You can say that. I was going to say attributed to might be a better word to say. The percentage of variation in y that can be attributed to a variable x. And remember, I could also say my response variable, right? The percentage of variation in my response variable that can be attributed to my explanatory variable. So remember, those are our explanatory and response variables. Response y, explanatory x. I can also get an r value from this, right? R is the square root of 0.132, which is, so let's go ahead, we can just do that with our scratch pad on our calculator. And that value is the square root of 0.132. So we have an R value of 0.36, which tells us that the relationship is moderate. Like, it's not weak, it's not strong. I would just say it's moderate. If you'd say a moderately strong positive linear correlation between our explanatory variable hours dining and our response variable tip. So that'd be a great way to explain what's going on with this R value. So let's go ahead and write that 3 approximately. They didn't ask us for that, but I just wouldn't feel good about it's such an important value when you're doing least squares regression. It tells you so much that I just don't feel comfortable calculating. Okay. All right. Do these data provide convincing evidence of a positive linear relationship? So here we go. This is, if you're asked for convincing evidence, your brain says, I need to perform inference. I need to do a hypothesis test. Because that's what you're doing when you're finding convincing evidence. You're finding convincing evidence when you're doing a hypothesis test. Good grief. Backwards words. All right, here we go. So we're going to go through phantoms. So our parameter of interest is you want to know what the true slope of the regression line relation relating dining time, length of stay, I guess. And tip amount. You want to know what is. That's a poorly written sentence. I apologize for my grammar. Should never put is at the end of your sentences. But there we go. Fantastic. We know our parameter. Let's make a hypothesis test. So, if there is really no relationship, or not, we would like the slope to be positive. That would show that the longer people stay, the more they tip, right? So if they don't tip more the longer they stay, then the slope should be 0 or less than 0, right? So we're going to say our slope, and the parameter that we're using for that is beta. Yeah. Let's see. it's good enough for it to be equal to 0, right? So then our alternative hypothesis would be that beta, is greater than 0, right? We want our slope to be greater than 0. Okay. And it might be nice to add the true slope beta here. Then we've defined our variable. All right, for A, so long for this, but it's okay. L. Does we'll go L. I guess that works. The data appears to have a linear relationship based on the residual plot. Let's look at that. I mean, I said it because obviously that's what's going to happen if they want us to perform inference. I don't think they would have given all of this if we're not going to perform inference, but hey, let's look at it and see. On this residual plot, do I see any type of weird pattern? It looks fairly good. I don't see any curvilinear type pattern. So fantastic. All right. We're gonna assume we can assume that one group's dining experience does not affect another's in terms of length of stay or tip, unless they're on Yelp. Then it can get ugly. Even though you can just get bad Yelp review, which makes it pointless. Cancel your account. Normal. It's all lies. All right, independent. We can see from the all right, so our normal probability plot that we have right here is telling me that it looks like there is a fairly linear relationship between our expected z-score and residual, so we can assume the data is approximately normal. It's right on. Not between what I think. Wow, I went to phantoms. I saw an N, and so I said, T must be next. We're going lighter. E. This one is equal. This one's the weirdest one to remember, right? E stands for equal, which means that the standard deviations are approximately equal, right? That was that picture that I showed you with all the weird normal distributions on the regression line. So standard deviations. Equal, and remember the way that we're going to tell that is we're looking at these. We're looking here at our actual scatter plot, and remember we're looking for any sort of fan pattern, right? If you see the data points very close together, or say the distance from each other on either side of your regression line gets larger and larger and larger and larger, then that's not going to work. Then that would put up a flag and not be able to continue. And it looks like they're fairly random. There's not any sort of clear pattern. Which means that overall the standard deviations are probably going to be fairly similar. And then R, the data comes from a random sample. Boom. A is done in our phantoms. Yay. N. We are going to do a t-test or slope. We will perform t-test. Okay, which means we need to get us a test statistic. T is going to be beta minus beta sub 0 divided by the standard deviation, or the standard error of our slope. And might that be? This is our slope right here. Okay, so in our case, our slope was, I'm going to go all the way back up here real quick. It was 0.03013. Wow, that's not what I just said. 0.3013 minus our hypothesis slope is 0, right? All divided by our standard error of our slope, which is, it's amazing that I can have fun. I'm enjoying myself right now. These problems all coming together quite nicely. All right, here we go. Standard error of our slope is right there, 0.02448. We'll put that into our handy-dandy calculator. Sorry, I don't have my table handy. And we will get 1.23. You can also find this value. So it's good to be able to calculate it. In this case, it's nice to see that it matches that computer output for T. Okay. You can use this value right here for your p-value, but it is always going to do a two-sided test. This computer output is always going to give you a two-sided test. So it is assuming that your alternative hypothesis is that beta naught is not equal to 0. So you have to cut it in half if you're going to use it. But rather than do that, why not just use the skills that we have and go to our T distribution? Okay. Degrees of freedom. It's going to be n minus 2. How many degrees of freedom? Should check that first. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is our size. So we're going to use degrees of freedom equal to 12 minus 2 is 10. Let's use an alpha level of 0.05. And now let's go ahead. Okay, so 10 degrees of freedom. .05. See what we all find our. Let's find our test statistic value in here. 1.23. All right. So at 10 degrees of freedom, 1.23 is in between here. So our probability is between 0.15 and 0.10. I think sometimes what happens is I become so dependent on the calculator that my brain forgets how to do it old school style, right? And so there you have it. So what are we going to do? So the probability is going to be between 0.15 and 0.10. And now we can actually go to this output and we can know exactly what it is. So our p-value, so there's one way to do it. Or we can go ahead and take this value that I pointed at here and divide it by 2 since it's a two-tailed test. 247 divided by 2, which turns out to be 0.1235, which is indeed what we expect it to be. Either way, we get it. If we do it this way or do it the other way, we will wind up failing to reject our null hypothesis. So we don't have convincing evidence that they actually do tip more when they stay longer. So we're going to fail to reject because we did O here. We're going to make a decision by failing to reject. I always say the null hypothesis, and it is so much quicker to just write that. And we can say we're going to use the S part. Don't forget the S. It's very important that you state your conclusion in context. So we do not have convincing evidence. Also, please be careful that you do not just say there is not a relationship between the two, or that there is not a positive relationship. You have to say there is not convincing evidence. We don't know that for sure. We could get a whole other sample. We could have gotten a weird sample, right? We could get a whole other sample and actually wind up rejecting the null hypothesis, right? So just for this particular circumstance, we have evidence. You can't say that, you can't make any overreaching claims. We do not have convincing evidence that customers tip more when they stay longer. We could have done this whole thing calculator-wise, is what I was looking at. We have this data here. We can make our calculator do all of this if we were to input time and tip into our calculator, and then use menu. Right, we would input time and tip into a list page, a listen spreadsheet page, and then we would go to stat tests, and there is a linear regression t-test. We would put in that x list would be length of stay, our y list would be tip. It will actually save our regression equation for us so that we can write that down, and then it gives us all of that output for our for whatever hypothesis we're testing. So it's really nice. So if you're just given a table of data, you can do all of it using your linear regression t-test, which is nice, especially for, I believe it is much nastier to do in a TI-84. The TI inspires are super, super good for statistics. They're pretty common. So that's it. That was 12.1. 12.2 is really, really not bad. Simple, especially for someone with a decent math background. That's logarithmic transformations. So we'll look at that tomorrow, and we'll be done with it. That's pretty much it. That's my last lecture.